Hello, you students of calculus. Today we're going to be working with trigonometric substitution. Try that again. And our objective is to use trig substitution to solve an integral and then use integrals to model and solve real-life applications towards the end of this lesson. Okay, but first let's talk about trigonometric substitution and what we're going to be doing here. So the trigonometric substitution, it's used to evaluate integrals involving the radicals, the square root of a squared minus u squared, square root of a squared plus u squared, and the square root of u squared minus a squared. Now, you might be thinking, well, this looks very familiar. We already know these antiderivative identities, and we kind of have seen antiderivatives involving these things, but we're going to be working with ones that can't be specifically solved just by applying those identities. So we're going to have to do a little legwork. Now, the objective with trigonometric substitution is to eliminate the radical in the integrand, basically substitute it out, and then use the Pythagorean identities to kind of simplify that. So, for example, if a is greater than 0, we're going to let u equal a times the sine of theta, where, well, that value of theta is between negative pi over 2 and pi over 2. Then a squared minus u squared is just going to be the square root of a squared minus a squared times sine squared theta, which is equal to, well, if you use that trig identity, we know that sine squared theta is going to be cosine squared theta plus 1, and we can also factor out an a squared here. So this becomes the square root of a squared times 1 minus sine squared theta, which we know, I guess, 1 minus sine squared theta, that's just cosine squared theta. So this is going to be a squared, square root of a squared, times cosine squared theta. I'm taking the square root of two things that are being squared, so I'm just going to be left with a cosine theta. So the way that we simplified, and I guess we need this note here for the value of theta, we have to keep in mind that we're working with cosine, so cosine of theta is going to be greater than or equal to 0 on this interval, negative pi over 2 to pi over 2. Okay, now, we'll go back to how we found this value for u in a little bit, but the way that we simplify these things, you're gonna, like in these problems, you're gonna have something like, I don't know, dx over this, for instance, and then you can substitute this a squared minus u squared, but we were wondering, where the heck do you get u squared equals a squared times sine squared theta? And that stems from applying the Pythagorean theorem and using some trig on a right triangle, kind of like you would have done in Algebra 2 towards the end, or maybe some pre-calc. So, basically what you're going to be doing in these problems is setting up a right triangle, putting values where they belong, and then using some trigonometry to kind of simplify those. So your textbook basically gives you these identities and these values, what you need to use in each case, but I want to talk about how they're found. So, for integrals involving a squared minus u squared, and we're going to keep, they say let u equal a times sine of theta, and we're going to talk about how that's found. Okay, so when you're working with this, you notice that it's kind of like the Pythagorean theorem. We have the square root of some quantity minus some other quantity squared. Both of those are being squared. Well, you must know, I guess normally you would see a squared plus b squared plus c squared, excuse me, a plus squared plus b squared equals c squared. And then if you were doing, well, then you would be solving for one of the legs. If you're taking the square root of something squared minus something else squared, you know that this must represent, well, this a value must be the leg, the hypotenuse, because you're taking its value, subtracting some other quantity. So we can set up a right triangle here, kind of plug in what we know here. So we know that a has to be the hypotenuse because, well, we're doing a squared minus some quantity squared. And this u squared must represent some other leg. We could let it be either leg, but in this instance, when we're working with that u, for all of these types of problems, that's going to represent something that involves an x more than likely, or a variable, I guess. So we're just going to put them on this leg, just to keep that uniform. So whenever you have a u or something involving a variable, since u represents like a variable thing, we're going to put it on the right side here. And that means, well, this leg has to be a squared minus u squared, or the square root of a squared minus u squared. So if we throw in a theta there, then we know, well, if we are trying to find some quantity that relates u, we know that if we do, well, let's see here, sine of theta is opposite over hypotenuse. If you need to write these to help you down, SOHCAHTOA, right? Sometimes I do that to help me out. We know sine is opposite over hypotenuse, so we know sine of theta equals opposite over hypotenuse. Well, that would be u over a, which means that u, if we solve for u, we're going to get u equals a multiplied by a times sine of theta. So that's how we get this value. Now, if that's the case, then, well, this square root of a squared minus u squared, if we substitute that u in, we're going to get a squared minus a times sine of theta. And then if we simplified this in a similar manner like we did up here, if we simplify that in a similar manner, we are going to find that, well, the square root of a squared minus u squared is going to equal a times cosine theta. Okay, where our value for theta is between negative pi over 2 and less than or equal to positive pi over 2. Okay, so in any of these problems, we're basically going to set up our right triangle, place our values, and then kind of use this right triangle to help us solve it. But for right now, we're just going to get these, I guess you want to call them shortcuts, but we'll see in an example. I'll actually work it out by hand what would happen if we didn't just plug in right away. Okay, so let's set up our right triangle. At least I'll set up this one down here. Theta, theta. All right, so for integrals involving a squared plus u squared, well, if I'm taking the square root of some quantity squared plus some other quantity squared, we know, and I'm taking the square root of that, that should be the hypotenuse then. So we know the hypotenuse is going to be a squared plus u squared. And keep in mind we said that our u is typically going to go on the right here since a and u are going to be our legs. Well, this would be u, this would be a, which would imply that if we're trying to relate some quantities u and a using theta, well, we know that this is going to be the opposite of theta. This is the adjacent one of theta. Well, what involves opposite and adjacent? That's tangent. So we know tangent of theta is going to equal u over a. We solve for u there, and we know that u is going to equal a tangent theta. So that's how you kind of come up with these substitutions you're going to plug into this. So u is going to equal a times tangent of theta, and then, well, if we substituted that in, you would have a squared plus a times tangent theta squared, which would be a squared tangent squared. You'd simplify that, and you'd find that, well, that a squared plus u squared is going to equal a times secant theta, where, well, once again, we're on this interval negative for pi. Negative pi over 2 is less than theta, which is less than pi over 2. Okay, so kind of use these triangles, set them up, plug them in, and then these identities that I'm going to highlight here, you can kind of look in your notes and just recognize what these are going to be. However, if you ever forget them, oh, a squared minus u squared should equal a cosine of theta, you can always just plug in your identity and then simplify by using some trig here. And you should end up with the same thing. So if you forget those, that's no big deal. It just saves you a little bit of time if you can remember them. All right, so for this last one, we have some quantity squared minus the square root of some quantity squared minus another quantity squared. Well, if this is the Pythagorean theorem kind of thing, we know that, well, this first quantity has to be our hypotenuse if we're subtracting the other quantity squared. So our u squared is going to go on the hypotenuse here. So this just becomes u, I guess I should say. And then, well, our a, we're going to keep that on the lower leg like we've been doing. And lastly, we know that this other leg has to be the square root of u squared minus a squared. So we want to relate these quantities u and a. What are the things? Well, if this is our theta, we know that a is going to be adjacent, and u is going to be the hypotenuse. What involves the adjacent and hypotenuse? And that's cosine. So cosine of theta is going to equal adjacent over hypotenuse a over u, which implies that u is going to equal, hold on, I made a mistake in my notes, but we're good on here. So if we solve for u, we'd multiply by u and then divide by cosine of theta. So we would get u equals a over cosine theta, which is really like saying a times 1 over cosine. We know that 1 over cosine is secant, so we know that u is going to equal a times secant. theta. Okay, so keeping that in mind, u equals a times secant theta, then we have that the square root of u squared minus a squared, again where u squared is some variable x, a squared is some value, some constant being squared. Well, that's going to equal plus or minus the tangent of theta, where, well, we're going to have these values. Theta is either going to be between 0 and, or I guess it's going to be greater than or equal to 0, less than or equal to pi over 2, or it's going to be greater than or equal to pi over 2 and less than pi. So we have this. 0 is less than or equal to theta, which is less than pi over 2. Or theta could be greater than pi over 2 and less than or equal to pi. So kind of on this interval. Now you want to use the positive value. Use the positive value of that statement if u is greater than a. And then you want to use the negative value if the opposite is true. Use the negative value if u is less than negative a. Less than negative a. Okay. So we kind of have these identities. I guess, I don't know if I want to call them identities. We have these substitution values. That's a better name for them. And we're going to be using these when we can't just apply an integral identity, I guess, like we could have before. So let's move on to an example. We want to do trig substitution for a times sine of theta. Okay, now, you would look at this dx over x squared times 9 minus x squared. Well, your a would be 3 and your u would be x. And you might think, well, this looks like an arc sine, doesn't it? dx over the square root of 9 minus x squared. But that x squared in the denominator kind of throws things off. So we have to use trig substitution here. So let's just set up our right triangle. And we know that it's going to involve this radical here. Our goal is to get rid of that radical. So set up our theta, our right angle. And we know if we're taking some quantity minus another quantity squared, well, this value has to represent something in the hypotenuse. Well, what squared is 9? That's 3, so that's our hypotenuse. We're subtracting x squared, and since it involves an x variable, this is going to be our u, which we're going to typically keep on the right side. So our u would just be x. And then our other leg has to be the square root of 9 minus x squared. Okay. Now you could recognize that this is in the form of a squared minus u squared, and you could just simply apply that and know that, well, the square root of a squared minus u squared is going to be that a value times cosine of theta. We'll get there eventually. I want to practice using this because we're going to have to use it in the end anyways to substitute in some values and simplify things. So we know, well, we want to involve this x and this 3. We know, well, the thing that involves the opposite in the hypotenuse is sine theta. So we know that sine theta equals x over 3, which implies x equals 3 times sine theta. Now we want to get rid of, we're substituting all the x's out. We want to substitute the dx's out as well. So what is dx going to be if x equals 3 times sine theta? And we know that dx is going to equal 3 times cosine of theta, d theta. Okay, we're going to plug in those values, and then I guess we also know a couple things. We know that the square root of 9 minus x squared, well, if we were to plug in 3 sine theta for x, we'd eventually get to the conclusion that we should get 3 cosine theta for that radical value. Okay, now you can certainly go back, use those rules 1, 2, or 3, kind of plug these in, or you can kind of just figure it out on your own. You don't. That's what's nice, is you don't have to memorize these. If you know your trig well enough, you can kind of just work them out on your own. So we're going to plug these values in. We know that the integral of dx over x squared times the square root of 9 minus x squared equals, this is the same as if we were to substitute in those trig values. This is the same as, well, dx is 3 cosine theta d theta over x squared, and keep in mind that x is 3 sine theta, so this is 3 sine theta squared times, well, 9 minus x squared, we know that that right here is going to be equal to 3 cosine theta. Okay, so let's just simplify some things a little bit. This is the same as, well, technically we're going to have all these coefficients, 3 over 3 times 3. Well, that's 3 over 9, which is the same as, well, I guess, hold on, we gotta simplify this first. This is technically 3 cosine. I'm getting ahead of myself, and that would have been wrong. Over, we square this value, it actually becomes 9 sine squared theta, 3 cosine theta. Then now we can apply that, simplify this down. Well, we're taking 3 and dividing it by 27. That's the same as 1/9. We can factor out that 1/9. This is the same as 1/9 times the integral of, well, what's also going to happen here is these cosine theta divided by cosine theta, that's going to reduce. I'm going to be left with just d theta in the numerator, and then I'm left with sine squared theta in the denominator. Okay, well, what do we do at this point? Well, we know that 1 over sine squared is the same as cosecant squared. So this is 1/9 times the integral of cosecant squared theta d theta. Okay, and we can actually do that antiderivative. We know that the antiderivative of cosecant theta is just negative cotangent of theta. So we're going to have, well, negative, and then we have that 1/9 up front. So negative 1/9 cotangent of theta plus c, because it's an indefinite integral. But we still want everything, since our original integral is in terms of x, we want everything here in terms of x. And this is where we have to go back to our triangle, because we don't have anything up in this right-hand corner that tells us, well, what the heck cotangent of theta is going to be. But that's where our triangle comes in handy. What is cotangent of theta going to be? Cotangent of theta, well, we know that cotangent of theta is just the reciprocal identity for tangent. So it's basically, we know that tangent's opposite over adjacent, so cotangent is going to be adjacent over opposite, which tells me it's going to be, well, cotangent of theta is adjacent over opposite. It's going to be the square root of 9 minus x squared over x. So go back up to that triangle, plug in that identity. This is going to be, well, negative 1/9 times, we know that cotangent of theta, using that right triangle above, is going to be 9 minus x squared over x. Put that in parentheses plus c, and maybe just simplify a little bit. This is the same as negative square root of 9 minus x squared over 9x plus c. And that's all that takes. It's actually not too bad. It's kind of a little pre-calcy, I guess, if you want to think of it like that. We're using some right triangles, just applying some trigonometry. Okay, so in example 2 here, we have dx over the square root of 4x squared plus 1. You might recognize, well, this is the form of, well, u squared plus a squared. U squared plus a squared. And if you recognize that and you already know the identity, you can certainly go ahead and do that second rule. But let's set up our right triangle anyways, practice how this is derived. I'll use a different color to distinguish it from the previous problem. So we have our right triangle. We have, if we're working with 4x squared plus 1, and we're doing the square root of that, well, both of those have to be our legs. We know that our u is going to involve the x variable, so we're saying, well, what squared gives me 4x squared? And the answer is 2x. Our a value is going to be what squared equals 1, and the answer is 1. And our hypotenuse has to be then the square root of 4x squared plus 1. Here's our theta. We want to relate the quantities x and 1. So we know, well, that's going to be the opposite over the adjacent. It's going to be opposite over adjacent, which is tangent. So we know that tangent theta is going to equal 2x over 1, which, well, that's simple enough. Tangent theta equals 2x, or you could say x equals 1/2 tangent theta. We can just leave it like this. Okay. Actually, you know what? Tangent, we'll solve for x. X equals tangent theta over 2, which means that dx is going to be, well, what is the derivative of 1/2 times tangent? We know that the derivative of tangent is secant squared, so this just becomes, well, 1/2 secant squared theta. Don't forget the d theta. And now we can just go ahead and do some substitution, keeping in mind, well, since this is in the form of a squared plus u squared, or u squared plus a squared, we know that addition is commutative, so the order doesn't really matter. We know that the square root of 4x squared plus 1. If we were to just plug in our x value, we would eventually simplify this and find that, well, this is just going to be the same thing as a times secant theta, which means that the square root of 4x squared plus 1 is just going to be, well, a times secant theta. It's just going to be secant theta. Okay? So go ahead and plug these values in. Dx we know is 1/2. We're going to write it in the numerator. It's going to look a little weird, but that's okay. 1/2 secant squared theta d theta over, well, this whole quantity we know is going to be equivalent to secant theta. Remember, it's a times secant theta for that. Well, we can simplify this a little bit, and we're doing the integral of this. Don't ever forget that, times d theta. All right. I can factor out that 1/2. Then I still have a secant squared theta over a secant theta. That's just going to leave me with 1/2 times the integral of secant theta d theta. And we know the antiderivative of that. That's just going to be 1/2 times the natural log of secant theta plus tangent theta plus c. Now we have to go back up. Well, what is secant theta? What is tangent theta? What are those values in terms of x? We have to go back up and plug in those values using some trig identities. Well, secant we know is 1 over cosine, so it's the reciprocal of the cosine identity. Cosine is opposite over adjacent, or excuse me, it's opposite over hypotenuse. So we know that secant should be hypotenuse over opposite. This is going to be the square root of 4x squared plus 1 over adjacent. Goodness, have I been saying the wrong thing? Maybe I should just write this down. SOHCAHTOA. SOHCAHTOA. All right. We know that secant is the reciprocal identity for cosine, so instead of it being adjacent over hypotenuse, it's going to be hypotenuse over adjacent, which is just going to be the square root of 4x squared plus 1 over 1, which is, yeah, the square root of 4x squared plus 1. Okay, now we're adding tangent. We know tangent is opposite over adjacent, so that's just going to be 2x over 1 or 2x. Absolute value of that plus c. Think, well, can I drop the absolute value signs and put them in parentheses? And the answer is no, because, well, you could still have a negative value here potentially. All right. So we're just going to leave this as it is. This is our antiderivative. Okay, that one's not too bad. Now, however, what would have happened if I just... Remember, you can still do these if you don't know that this value right here is going to be this value, because, well, you could just know that from above we would find that x should be tangent theta over 2. You plug that in, you get the square root of 4 times tangent theta over 2 squared plus 1. Simplify that. That's the same as, well, you square both of those. It's going to be tangent squared theta over 4. 4 divided by 4 is 1. So you're just left with tangents, the square root of tangent squared theta plus 1, which you know by the Pythagorean identity that that's just going to be secant squared theta. Do the square root of that, and you get, well, lo and behold, secant theta, which is what we knew it would be. Okay, so if you ever forget, just plug in that value for x and just use trig identities. You'll end up at the same spot anyways. So we'll move on to example 3, and this will be the last example in this section of the video. Okay, trig substitution again. So we have this thing, and we can't just evaluate it using basic, well, integration identities, I guess, if you want to call them that. So we're going to, again, set up our right triangle. But this one seems different, doesn't it? And I guess before I got a little bit ahead of myself. This one doesn't just have the square root of something. But keep in mind, how can I rewrite something to the 3rd halves power? We know it's going to involve a radical, a square root. It's going to involve something with a 3rd power. So we can rewrite this. Keep in mind, you can rewrite this as x squared plus 1. The square root of that, all of that, to the 3rd power. So we can still evaluate this with an x squared plus 1. And keep in mind, well, that's definitely going to be the second rule, a squared plus u squared. Set up our right triangle here. Set up our right triangle. Here's our theta. Well, we're looking at the square root of x squared plus 1. We know that that value has to go in the hypotenuse if we're taking the square root of 2 values that are being added together. This is going to be the square root of x squared plus 1. X squared is going to go here. 1 is going to go here. All right, now if we're trying to involve these values, and whoops, so this should just be x. My bad. That should be x. Now we're good. Okay, so we want to involve this side with this side. Well, we know tangent of theta is the one that's going to relate the opposite to adjacent. So tangent of theta is going to be opposite over adjacent. X over 1 is just x. So x is tangent theta. Dx then is going to be, well, the derivative of tangent is secant squared. So this becomes secant squared theta d theta. And, well, if we plugged in just x for that and simplified, we could eventually come to the conclusion, or keep in mind that this is just going to be a times secant theta for a quantity u squared plus a squared. So we have x squared plus 1. The square root of that is going to be equal to, well, 1 times secant theta, or just secant theta. So now we have all of our trig identities. We have our trig substitution values. Call them that instead. Plug them in. So dx, we know that that's secant squared theta d theta over x squared plus 1, the square root of x squared plus 1. Well, that's just secant theta, and we're cubing that, so secant cubed theta. This is going to simplify down to, well, the integral d theta over secant theta. Well, what do we know? That secant theta is the same as 1 over secant theta is the same as cosine theta. So this is the same as the integral of cosine theta d theta. What's the antiderivative of cosine? And we're saying what thing's derivative is cosine, and that's just sine. So the antiderivative of cosine is sine theta. And then once we evaluate this indefinite integral, we're just going to get plus c here. And this is going to equal, well, go back up to our triangle. What is sine of theta? Sine is opposite over hypotenuse. That's going to be x over the square root of x squared plus 1. So our final answer is going to be x over the square root of x squared plus 1 plus c. That is going to be our answer. We will get the remaining problems completed in the next video. I didn't do a great job of scripting these notes. I'm going to go ahead and write down a couple things alongside what each step is, just in case you're referring to the notes later, you understand that. That's all we're going to be covering in this video. The next video we'll finish these section of notes. Have a good day, everybody, and as always, stay safe out there.